Many of you might be familiar with the following quote from famous astrophysicist Carl Sagan: "We are made of stardust." For many, this might sound like merely a poetic exaggeration. But the fact is that our human connection to the universe is one that spans billions of years and connects each and every one of us to the very fabric of the universe. Every atom comprising our bodies, our blood, and our surroundings have their origin in one or more cosmic events in the universe. Hydrogen atoms in our bodies can be as old as 13.8 billion years, forming only shortly after the Big Bang. Carbon, oxygen, and iron atoms in our blood originate from a supernova explosion of a massive star, more than 8 times the mass of our own sun. Silver, platinum, and gold in our jewelry are primarily created in cataclysmic collisions of dead stars. But the question remains, how exactly are the chemical elements in the universe formed? And how has the chemical composition of the universe affected our lives here on Earth? The stars have been our guides for centuries. We have used them as navigational beacons to cross the oceans. In the age of seafaring, mariners relied on constellations as celestial roadmaps to chart their course across vast oceans. Navigators use the bright North Star Polaris to determine their latitude above the equator. Canopus, the second brightest star in the night sky, has long been used by sailors to navigate and sail to other worlds. If you are a sci-fi lover, you may know it as home to the planet Arrakis in the novel Dune. This is just one of the many examples in which stars have inspired our art and literature. The night sky, adorned with constellations, has become a canvas for our imaginations, giving rise to tales that transcend time and space. These stories have to transmit eons worth of knowledge to successive generations. For example, one of the most famous Greek literature works by Homer, the Odyssey, contains a wealth of astronomical information, giving references to the sun and moon, constellations, and planets, which constitutes an invaluable source of information on the state of Greek astronomical knowledge at the 8th century BC. Stars also evoke a sense of optimism in our lives, reminding us of the infinite possibilities that lie within the universe and ourselves. Their enduring presence, whether in the form of a faint twinkle or a dazzling sparkle, resonate deeply within the human spirit. But our connection to these beautiful balls of gas goes far beyond mere symbolism. It turns out that our exploration of the stars is also an exploration of our own cosmological heritage. Every element we have inherited on Earth that makes up everything we see and experience around us have their origin in the chemical makeup of stars. This fact has inspired me to become an astrophysicist, even when such a dream seemed difficult and far-fetched for a young astronomy enthusiast and a first-generation college graduate from a small country like Lebanon. I've been studying stars and their chemical compositions for the past 10 years to understand their role in the chemical makeup of the universe, as well as their evolution in our own Milky Way galaxy, and have been fascinated by how our lives are shaped by these entities. Every star, from its birth to its death, plays a profound role in the formation of the elements in the universe. This intricate phenomenon, known as chemical enrichment, started nearly 14 billion years ago, right after the Big Bang, and has continued unabated to this very day. Stars in their cosmic journey undergo a series of transformative stages that culminate in the creation and dissemination of the elements that we see in the periodic table today. This dispersion of elements back into the universe serves as the foundation for the creation of new stars, planets, and celestial bodies. In fact, our own solar system, which formed nearly 4.5 billion years ago, is a direct outcome of this chemical enrichment process, forming from the concentration of elements that gradually accumulated in our own natal birth cloud, a cloud of gas and dust that contains the raw materials necessary for the creation of our planetary system. Now, what's interesting about this process is that every star, including our sun, preserves the entire history of their ancestors that were born and have died before them. Stars, like us, carry the DNA and genetic blueprint of their ancestors. We can observe signatures of this DNA by pointing our telescopes toward the stars. Our telescopes are equipped with an instrument called a spectrograph that can decompose the light from the star into its constituent rainbows. These rainbows encode a wealth of information about the physical and chemical state of the star. Our sun, as seen through a spectrograph, reveals these dark patches which tell us about the chemical elements that are found in their outer layers. Okay, but how do the stars form the chemical elements? Let's take the story of two of the most famous elements here on Earth, gold and uranium. The first step of the process starts right after the Big Bang, where the universe was made entirely of only three elements: hydrogen, helium, and a little bit of lithium. Many of the other elements were created inside the stars via a stellar process known as nuclear fusion, where light elements like hydrogen fuse together to sequentially form the heavier elements all the way until iron in the periodic table. You see, every twinkling star in the night sky is an individual factory that is constantly creating new elements, further enriching the universe. Beyond the 6,000 stars visible to the naked eye, there are trillions of other stars doing the same thing. In return, the excess energy is what causes the stars to shine. Now, the formation of the elements heavier than iron in the universe require more extreme environments, usually triggered by the end of a star's life. In the next steps, as the star's fuel runs out, it explodes into a supernova, infusing the universe with the elements it created during its lifetimes, and violently collapses. This process also creates very dense stellar remnants, or dead stars, known as neutron stars and black holes. But our picture of chemical element formation remained not well understood for many of the elements, including gold and uranium, and only recently, in 2017, did it start to become complete for the first time. I'm one of the astronomers studying the origins of the most heavy radioactive elements found at the bottom half of the periodic table. The exact events that are responsible for creating these elements and in what amounts remain shrouded by mystery for astronomers like myself. However, in 2017, a rare and unique astronomical event was observed by nearly every large telescope from Earth and from space. For the first time, we were able to detect signatures of two dead neutron stars collide and merge. This event provided crucial insights into the origins of gold and uranium. Picture this: two massive stars, born as twins, grow old together, die together, and eventually get locked into a gravitational cosmic dance for millions of years. After a while, these stars will collide and merge into a spectacular event known as a neutron star merger. Astronomers now believe that such events are responsible for creating most of the elements heavier than iron in the universe via a nuclear process known as the R process, or the rapid neutron capture process, where an atom, such as iron, gets bombarded with neutrons which it captures to create these heavy elements. The saga continues for several billion years until these newly formed elements eventually find themselves as part of an aggregating planet around a mid-sized star, the Sun, in one of the spiral arms of the Milky Way galaxy. Finally, gold and uranium are now two of the many seeds that have been implanted in the Earth's core. Therefore, the origins of the precious metals that you're wearing, like gold, or even the radioactive elements found at the core of the Earth, are from a stellar merger at least 4.5 billion years ago. But our story is not over just yet. It turns out that the understanding the origins of the elements has not only deepened our knowledge on the chemical origins of Earth's building blocks, but it has also been recently implemented in the ways we explore the possibility of finding life in the universe. While NASA missions have been discovering thousands of planets beyond the solar system, what constitutes a habitable planet, or a planet capable of harboring life, remains elusive to astronomers who are working hard to identify the conditions of life. Our questions range from investigating the presence of liquid water or an atmosphere to analyzing the planet's stability and longevity, as well as its chemical building blocks. But it turns out that the internal heating of planets by radioactive decay of elements, particularly uranium, is an essential driver behind geophysical phenomena that are crucial for the formation and sustainability of life. This phenomena fuels the intricate ballet of mantle convection that not only shapes Earth's crust, but is also fundamental for the recycling of essential minerals and nutrients. This perpetual motion beneath Earth's surface influences the movement of tectonic plates, orchestrating the geological symphony that sculpts landscapes and creates diverse habitats. Therefore, as we search for life in the universe around other planets, we need to also look for their radioactive elemental content as a crucial life marker. What this tells us is that the exploration of the elements in the universe transcends the boundaries of astrophysics, influencing the very fabric of our own planetary existence. It underscores the interconnectedness between cosmic phenomena and life-sustaining processes, offering broader perspectives as we contemplate the possibility of life beyond our celestial home. These elements have played a significant role in our lives on Earth. Gold is highly valued for its rarity and beauty, and it has shaped our economies for centuries. It has not only served as a standard for currency and economic stability, but it has also been intricately interwoven into the fabric of art, religious artifacts, and societal hierarchies. Its gleaming presence has sparked exploration, conquests, and even the establishment of empires. On the other hand, uranium, the rarest naturally occurring element on Earth, possesses properties that extends its impact far beyond the realms of adornment. Its significance lies in its ability to unleash formidable nuclear energy, a power that humanity has learned to harness for constructive, as well as regrettably destructive purposes. The controlled fission of uranium isotopes serves as the cornerstone for the production of nuclear energy, a potent source that has the ability to meet our growing global energy demands. This technological application, while offering promising solutions to our energy needs, also poses challenges, as a specter of nuclear proliferation and environmental concerns loom large. The dual nature of uranium underscores the delicate balance that humanity treads in weaving the elements inherited from the stars for our own benefits. From powering cities to the ominous shadow of nuclear weapons, uranium's role in shaping the trajectory of our civilization is both awe-inspiring and cautionary, prompting reflections on the ethical responsibilities that are tied to the manipulation of the elements. Embarking on the odyssey of elemental cycles together has taken us on a captivating journey across time and space, where precious elements like gold and uranium undergo a transformative saga from the fiery hearts of stars to the intricate tapestry of human civilization. In the course of time, the geological odyssey of gold and uranium intersected with the narrative of humanity, capturing its imagination and scientific inquiry, becoming the symbols of power and wealth they represent in our society today. From the Big Bang to nuclear fusion inside stars, to supernova explosions, to two dead neutron stars that collide and merge to create these rare elements, to stardust from which our own solar system was formed. These elements have played an integral part in Earth's history, quietly shaping its landscapes as well as its geological and societal identities. This is the story of merely two elements in the universe that have shaped our lives here on Earth. But similarly, every other element in the periodic table has its own inspiring and captivating journey in the universe. In the end, I leave you again with the words of Carl Sagan. The origin and evolution of life is tied to in the most intimate way to the origin and evolution of stars. Therefore, the next time you look up at the night sky or wear a piece of jewelry, remember, you are not just observing or adorning. You are actually embracing a piece of the cosmos. Our connection with the stars goes far beyond the romantic. It's scientific, it's historic, it's human, and it's a call to appreciate and protect the elements of our world. Thank you.